Okay, class, picking up where we left off at with problem number 9. A loan has a nominal interest rate of 4% and the interest is compounded weekly. Without doing any calculations, would you expect the effective interest rate to be higher or lower than 4%? Explain. I would expect it to be higher. Compound interest earns more than simple interest. So, the effective rate would be higher. It says here, refer to question 9 and calculate the effective interest rate. So we will have E is equal to 1 plus R over N to the N power minus 1. Where our rate is 0.04, which signifies the 4%, and N is equal to 52 because there's 52 weeks in a year, so it compounds weekly. So we will have E is equal to 1 plus 0.04 all over 52 to the 52nd power minus 1. So this would equal to 0.0408 when you put in your calculator, which is 4.08%. So that is the effective interest rate. Okay, number 11. It says find the future value after 1 year for an investment of $10,000 at 4% compounded weekly. Okay, so we have P is equal to 10,000. R is equal to 0.04. N is 52. And T is 1. So we have A is equal to the principal, which is 10,000, times 1 plus 0.04 all over 52 to the 52 times 1 power, which we know would be 52 power. And that would give us $10,000, 407.95. 10,407,095 and 95 cents. Okay, now we move on to the next problem. It says divide your answer to question 11 by 10,000. So our answer to question 11 was $10,407.95. So now they want us to divide this answer by 10,000. What do you notice? This will give us 1.0408. Now, if we take off the 1, let me write it down here. If we took off the 1, this would be 0.0408, which would be 4.08%. So it would be the same as the effective rate, the effective interest. So, if we look at problem 13, now let me just explain this. The reason why this is the same as the effective interest, all this is saying is this here. This 1 signifies that you added $10,000 back to the interest that you received on problem number 11. If you look at problem number 11, your actual interest from this problem was $407.95. Now, when we get over here, by putting that 1 in front of the decimal, that would mean we would have 10,000 plus the interest we got on the previous page. So that is why the 1 is in front. But if we just wanted the interest, this would be the interest rate here. Now, 13. It says comparing investments is a very important part of any financial strategy. Which savings account is a better investment? 6.2% compounded daily, or 6.25% compounded semi-annually. There are different ways you could approach this, so make sure you show all work and explain how you made your decision. Now listen, first thing, we know compounded daily, we're going to use a regular year, which would be 365. I'm going to write this up here, 365 days. Semi-annually means twice, because we know it's every 6 months, so that means it will compound twice. So now if we do the effective rate, we have 1 plus r divided by n to the n power minus 1. So we subtract the 1 off just to see the actual interest rate. So now we will have E is equal to, it said it's 6.2% daily. So let's write that over here. R is equal to 0.062. And the N is 365 with the number of times it compounds. So now we will substitute 1 plus 0.062 all over 365 to the 365th power minus 1. So E will be approximately 0.06396, which would be approximately 6.396%. Now this is the daily calculation. Now we want to do the semi-annually. With the semi-annually, is R is equal to 0.0625 and N is equal to 2. So we will have E is equal to 1 plus 0.0625 all over 2 to the second power minus 1. When we put this in our calculator, it'll give us 0.06348, and then we can make this into a percent, which is 6.348%. So this is higher. Now, just a little bit more of an explanation. When I told you all up here about getting the 1, and this is the actual effective interest rate, this formula here signifies that with the subtracting of 1, well, we would just see the effective interest rate instead of adding back in the principal. That's what this minus 1 does. It subtracts out the principal. Okay, so now we move on to problem 14 on the next page on 226. Now, on this page, it says interest compounded continuously. The goal of the remainder of this lesson is to see if we can figure out what happens to the compound interest formula when the number of times that interest is compounded per year gets really, really large. Large to the point that in essence, interest is being compounded every instant of every day. Wow. As you know, the compound interest formula is A equals P times 1 plus R over N to the NT power, where N is the number of times per year that interest is compounded. To rewrite this formula in a form that makes it easier to decide what happens when N gets really big, we're going to introduce a new variable U, which will be defined by U equals N over R. First, solve this equation to find a new name for N. So we will have R times U, and then that will give us, well, actually is U equals N over R. And then we will try and get N by itself. So we're going to multiply each side by R. So this will give us N is equal to U times R, because these R's will simplify out. Okay, now replace N in the compound interest formula with the new name for N that you found in question 14, and simplify to show that the formula becomes A is equal to P times 1 plus 1 over U to the URT. So we will have A is equal to P times 1 plus R over N to the NT. Now we will substitute. A is equal to P times 1 plus R over, now remember N is UR, to the power of URT. So now, we will simplify out the r's. So it would be A is equal to P times 1 plus 1 over U to the URT power. So this is how this formula is derived. Now we come here to 16. It says explain why this can be rewritten as A equals P times 1 plus 1 over U to the U to the RT. Basically, using exponent rules, here we will multiply exponents. In the example, we had A equals P times 1 plus, well, we had that bracket here, 1 plus 1 over U to the U to the RT. We'll multiply those exponents, and it'll be A is equal to P times 1 plus 1 over U to the URT. That's basically what it is. Now it says, remember that U equals N over R. What happens to this fraction when N gets really big? Remember that R is the interest rate and it can't change. Since N is the numerator, as it gets really big, so will U. Okay, now we move on to the next page, to problem 18. Now with problem 18, it says, here's a summary of what we learned in questions 14 through 17. The compound interest formula can be rewritten in the form below. And as we make the number of times that interest is compounded per year get larger and larger, the variable U in that expression gets larger and larger as well. So next we'll study what happens to the expression inside the brackets when U gets larger and larger. And we'll find that we can find a much simpler form for this formula. Okay, using a calculator, it says fill in the table below, round to 3 decimal places. What can you conclude about what happens to the value of 1 plus 1 over U to the U as the number of compounded period tends to infinity? Okay, class, I took the liberty of filling this out with these values here, and when you put them in the calculator, you will get the values that's shown here. Now, what this states is the value tends to 2.718, because as you notice, it continues to go up to 2.718. Now, of course, you could pause the video, put this in your calculator, and you will see rounded to 3 decimal places, you will get these values. Now 19, the number that you should have found in question 18 is about 2.718 and is denoted E. Actually, E is irrational, so its decimal equivalent neither terminates nor repeats. What is the result of the compound interest formula above when the number of times interest is compounded gets larger and larger? In this case, we say that interest is compounded continuously. You could think of this as the interest being compounded every instant of the day. So it'd be A is equal to P bracket 1 plus 1 over U to the U bracket to the RT. Now A would equal to P times the bracket of E to the RT, because we proved that 1 plus 1 over U to the U is actually E. So then our new equation is A is equal to P times E to the RT. Now I would tell you this. This is the equation that was derived by going through this process. And we will use this equation when it's time to do interest compounded continuously. We won't have to go through this process again. We will basically just be using this formula instead.